Good morning, everyone, and welcome to another live Quanser user webinar. I'm Murtaza and your host for today. In this webinar, we will have Dr. Montanaro, who is currently a senior lecturer in autonomous systems and control engineering with the School of Mechanical Engineering Sciences, University of Surrey in Guildford, UK. The scientific results he has obtained up to now have been the subject of more than 70 scientific articles published in peer-reviewed international scientific journals and conferences. Dr. Montanaro will present his work on the development and validation of advanced path tracking solutions using the Quanser QCar.
Welcome everyone and to this webinar. The title of this webinar is You Are on the Right Path, Approaches to Rapid Prototyping and Validation of Advanced Path Tracking Solutions. And as we are going to discuss shortly, the target of this webinar is to present some innovative path tracking solutions for autonomous scaled vehicles and their validation through the use of QCars made by Quanser. I am Umberto Montanaro, and I'm senior lecturer in control engineering within the School of the Mechanical Engineering Sciences of the University of Surrey. In addition, I'm also the director of the Surrey team for the control of a smart multi-agent system operating autonomously and synergetically, also abbreviated as S-Cosmos. S-Cosmos indeed is a new team at the University of Surrey dedicated to the control of autonomous systems and their cooperation to perform collaborative tasks. Examples of research topics of interest for our group include, but not limited to, path planning and tracking for autonomous systems and vehicle platooning. The work that is presented in this webinar has been made within the S-Cosmos team, which currently also includes two PhD students, Pietro Stano and Carmine Caponio, who are here today connected to this webinar and will participate to the Q&A session following this presentation. So, as previously mentioned, this webinar is dedicated to present a path tracking solution and their experimental validation. In order to make sure that we are all on the same page, these slides briefly report the objectives and the challenges for path tracking control solutions. So, if we consider an autonomous vehicle equipped with an hierarchical control architecture, we can clearly identify three key layers. The perception layer that provides to the vehicle information of the surrounding environment, the planning layer that is used for generating collision-free trajectories that the vehicle has to follow, and finally, there is the control layer that decides the commands to the actuators in order to perform a given driving tasks. And in this layer, we find path tracking controllers, which generates commands to follow the path decided by the planning layer, for instance, with a given speed profile. The design of path tracking control strategies is a challenging task, as the resulting control system must be robust, for instance, to several factors, such as vehicle nonlinearities and parameter uncertainties, for instance, in terms of cornering stiffness of the tire. Moreover, there is the need of robustness to the coupling of the lateral dynamics of the vehicle with respect to the longitudinal ones. On top of that, the experimental testing of a path tracking solution can be challenging and time-consuming. In these regards, car-like robots, such as the QCar, can be used to shorten the time of testing and validation of novel control solutions. In this general framework, the objectives of this webinar are threefold. First, we want to present the design of two path tracking control strategies that have been developed within the S-Cosmos team. Then the target is to discuss the implementation and the experimental validation of these strategies through the QCars that has been used as a platform for rapid control prototyping. And the last target is to compare the performance of the proposed solution with a set of algorithms taken from the open literatures. Also, these algorithms have been implemented in our lab and used as a benchmark control strategies. In terms of hardware, we have three QCars and a Quanser reconfigurable track. This slide briefly presents the points that we are going to discuss in this webinar. And as said before, the core part of the webinar is dedicated to the experimental validation of two novel path tracking control solutions that have been designed with two distinct methodologies. In particular, we will focus first our attention on a neural network-based enhanced model reference adaptive control, here abbreviated as NN-EMRAC. And then we will focus on the design and experimental testing of a deep reinforcement learning algorithm based on an expert demonstrator. For each of these algorithms, we will present first, briefly, their working principle with some design details. Then we will point out the key features or the unique aspects of each control methodologies that we want to test experimentally. And then we will discuss the experimental results through a set of key performance indicators, also abbreviated as KPIs. However, as the proposed control solutions require, in a way or another, the use of a dynamic model of the vehicle, before deep diving in each of the control algorithm, I want to briefly give you some details about the mathematical model of the QCar that we have developed along its experimental validation. Moreover, we will touch also briefly the control architecture that has been developed to host these control solutions. So let's get started. In terms of modeling, we consider as a control input the armature voltage to the DC motor on the QCar, here indicated as VA. The additional control input is the steering angle delta. The states of the vehicles are the longitudinal speed v, the side slip angle beta, the heading angle phi, and its derivative yaw rate. Furthermore, other states are the x and y position of the center of the mass of the QCar with respect to an inertial frame. The longitudinal dynamics have been modeled through this first-order linear system, while the lateral dynamics are captured by this third-order linear system. For these two models, the lumped parameters P1, P2, and P3, along with the cornering stiffness of the front axle and the rear axle, here indicated as CF and CR, have been estimated experimentally by using a two-stage identification procedure, as these parameters are those most affected by uncertainty. The identification procedure and the full experimental validation of the model that we have developed are reported in this paper, with the title Modeling, Positioning, and Deep Reinforcement Learning Path Tracking Control of Scaled Robotic Vehicles, Design and Experimental Validation, recently finalized by our group. Here, we just report two model validation results. The first one is related to the longitudinal dynamics and shows the evolution of the speed of the vehicle when the armature voltage is a step of 1.5 volt. The second plot instead is dedicated to the validation of the lateral dynamics and consider a step steer of 13.5 degree when the speed of the vehicle is 1.5 meter per second. For both plots, we note that the state evolution predicted by our models, here reported as a red solid line, will match the experimental data represented through a blue solid line. In terms of control architecture, instead, we can mainly identify three subblocks. The first subblock is a federated Kalman filter composed by two extended Kalman filters and a master filter. This subsystem is used to generate a more precise estimate of the vehicle states based on all the measurements provided by the LiDAR, encoder, and IMU sensor equipping the QCar. The second subblock, here denoted as tracking error generator, is used to compute the reference trajectory, including the reference heading angle phi ref, and the reference curvature indicated as a kappa ref, as well as the tracking error, including the error on the heading angle denoted as delta phi, and the lateral displacement, the lateral error, between the center of mass of the QCar with respect to the trajectory to follow. These errors are then, that are computed with this formula, are then sent to the last layer of our architecture, that is the control layer. In this layer, we find two controllers. We have a cruise control for imposing a desired speed and a path tracking controller, which can be either the neural network enhanced model reference adaptive control strategy or the deep reinforcement learning one. In terms of a key performance indicator used for comparing the different solutions that we are going to discuss in this webinar, we have defined three KPIs. The first two are used for measuring the closed loop tracking performance, and they are the root mean square error of the lateral deviation and the maximum error of the lateral deviation. Moreover, the control effort is measured through a third key performance indicator, which is the integral of the absolute value of the tracking action, here abbreviated as YACA, which is practically the integral of the absolute value of the steering angle. In all this formula, TF is the duration of the maneuver. So let's start analyzing the design and working principle of our first control solution, the NN EMRAC, the Enhanced Model Reference Adaptive Control equipped with neural network. But first, I would like to show you the neural network enhanced model reference adaptive control structure step by step. So if we think a classical control strategies in the state space domain, usually these control strategies are composed by two control terms, a feedback control term and a feed-forward control term, where the feedback gains Kx and Kr are usually constant and selected offline by practitioners. In the case of the standard model reference adaptive control algorithms, these feedback gain and feed-forward gain are adjusted or better adapted online through an adaptive mechanism such that the dynamics of a reference model are imposed to the plant, in this case, the QCar, despite parameter uncertainties, external disturbances, and eventually nonlinear term not considered during the modeling of the plant. The enhanced model reference adaptive control strategy extend or augments the classical model model reference adaptive control solution by adding two additional control terms, an adaptive integral action and an adaptive switching or sliding mode control action. And the gain for the integral action Ki and the gain of the switching action Kn are again made adaptive through an adaptive control law. Finally, the neural network NN, Enhanced Model Reference Adaptive Control, further extend the control action by equipping the classical and Enhanced Model Reference Adaptive Control strategy with the control action provided by a neural network to further improve the tracking of the reference model. As an additional note, I want to point out that the initial version of the Enhanced Model Reference Adaptive Control solution have been proposed around 2010 during my first PhD. However, over the year, I had the chance to extend the theory of the Enhanced Model Reference Adaptive Control in a different direction. And I also had the possibility to apply this theory to several engineering control problems, including the control of the electronic throttle body, common rail systems, and robotic manipulators. A version of the Enhanced Model Reference Adaptive Control algorithm was also used for path tracking, but not experimentally validated. In this webinar, we experimentally test via the QCar different Enhanced Model Reference Adaptive Control formulation, including also neural network. In terms of details on the control design, we have that the reference model has been selected as the nominal model of the QCar that we have presented previously in this webinar, controlled through an optimal linear quadratic control action, abbreviated as LQ. The state two controls are the lateral speed, the yaw rate, the lateral error, and the heading error. For the neural network, the activation function, we have selected as activation function the ReLU. Finally, it is important to point out that all the initial adaptive gains and the weights of the neural network are set to 0. Thus, in our design, we assume that we don't have any pre-knowledge of the plant that could have been used for initializing these gains. And somehow here we are considering one of the worst scenario, where the gains are all initialized at 0. The target of the experimental campaign is threefold. We want to first study the closed-loop dynamics with and without the neural network, and this also enable the second target. That is the evaluation of the effect of the neural network control action on the closed-loop tracking performance. Another target for the experimental analysis is the study of the dynamics of the adaptive gains. In terms of path, we have selected this infinity shape path to be performed with a constant speed of 0.6 meter per second, and this path is executed 3 times. Here we have some experimental data where the dashed black line is the reference model dynamics. And then we have the closed loop dynamics given by the Enhanced Model Reference Adaptive Control in green, while in red we have the output provided when the neural network Enhanced Model Reference Adaptive Control is used. And from these initial experimental data, we can already derive some interesting observations, some interesting remarks. First of all, we can note that the contribution of the neural network can improve the tracking of the reference model in a steady state. For instance, if we look at the steady state heading angle, we can see that there is an improvement of the reference model. But mainly, we can note that the neural network improves the tracking performance during the initial transient of the adaptive gains. And this is clear if, for instance, we look at the initial transient of the lateral error and the initial transient of the heading error. In terms of adaptive gains, here we have reported the evolution of phi and Cn for both the adaptive algorithm with and without the neural network, where phi is the integral part of the stack of a vector composed by the gain kx, ki, and kr and ki, that are the gains of the continuous part of our adaptive strategy. Instead, Cn is the adaptive gain of the adaptive switching control action. And these two plots shows that the adaptive gains are usually smaller when the neural network is used, and also with a smaller overshoot. The qualitative analysis that we have just presented is further confirmed by the study of the key performance indicators, which have been computed over the first cycle for 3 different speeds: 0.6, 0.7, and 0.8 meter per second. The analysis of the YACA shows that for 0.6 and 0.7 meter per second, the control effort required by the neural network enhanced model reference adaptive control is smaller than that required when the contribution required by the neural network is switched off, and this improvement is about 30%. And this reduction in the control effort is mainly because the initial transient, there are smaller error during the initial transient. Indeed, if we look at the the key performance indicator for the tracking performance, we see that the tracking performance improve with the use of the neural network, especially for 0.6 and 0.7 meter per second. Specifically, for 0.6 meter per second, there is a reduction of the maximum error during the initial transient of about 75%. While the reduction of the root mean square error is about 71% when the neural network contribution is switched on. For 0.7 meter per second, this reduction is 57 and 71% respectively. Now, these two videos shows the closed loop performance of the enhanced model reference adaptive control and the enhanced model reference adaptive control equipped with the neural network when the longitudinal speed is 0.6 meter per second. In this side picture is reported not only the path that we want to track, but also the instantaneous position of the center of the mass of the QCar, represented as a red dot, along with the heading error and the lateral error. So, when the enhanced model reference adaptive control with zero initial gain is used, initially there are some notable errors between the reference path and the actual path of the QCar. However, as the time increases, the adaptive gains evolve as previously shown, and the continuous adaptation of the control gains through the enhanced model reference adaptive control law improves the tracking performance. And it's important to remark that the improvement of the tracking performance over the time because of gain adaptation is a key aspect of adaptive control, which can make adaptive control solution outperform classical control strategies with the fixed gains. Instead, when the QCar is controlled through the neural network enhanced model reference, Now, when the QCar is controlled through the neural network enhanced model reference adaptive control, we can see that the initial errors between the reference trajectory and the actual trajectory reduce quite significantly. The improved initial transient response is due to the neural network control that over the initial transient provides a further adjusting control term to the overall control action. After the first transient, the adaptive gains and the weights of the neural network continue to update to provide closed-loop robustness to unmodeled dynamics, disturbances, and vehicle parameter mismatches. Now we can focus on the second control solution for this webinar, which is a deep reinforcement learning strategy equipped with an expert demonstrator. Again, to be all on the same page, let's briefly revise the working principle of a deep reinforcement learning based control algorithm by considering directly the learning architecture that has been developed for the QCAR. So, for the proposed solution, the controller or agent, as it is called in the framework of the deep reinforcement learning based control method, is a neural network which decides the action or control action based on a set of measurable quantities known in the literature as observation. The agent decides the action based on observations in order to complete a given task. In the case of the path tracking, the task to complete is the execution of the path with the smallest tracking error. In terms of action, we have selected in terms of action the ratio variation of the steering angle, or in other words, the derivative of the steering angle, while the adopted observations are the lateral error and its derivative, the heading error and its derivative. It's pointed out that the neural network is with its input and output is the one deployed on the QCAR and experimentally tested. Instead, the training of the neural network is done in simulation by using a deep reinforcement learning approach, which consists of utilizing the interaction between the agent and the environment. In the context of the reinforcement learning framework, the environment is the external system which interacts with the agent. In our case, the environment is composed by the QCAR along with the quiz control and the blocks for generating the reference path and the required error. And based on the action requested by the agent, the environment generates the observation. In addition to the observations, the environment also generates what is known as a reward signal, which is here indicated as R tilde, which is generated through a reward function. The reward signal is a kind of a measurement of the goodness of an action in a given state of the environment in order to complete a given task. The higher the reward signal, the better. In this framework, the neural network is then trained to maximize the cumulative reward of a sequence of episodes. So, from the description of the working principle of a deep reinforcement learning control approach, it emerges that the selection of the reward function is critical for the execution of the task. In our work, we have used an approach based on the use of an expert demonstrator to formulate the reward function. Specifically, our reward function is composed by four terms. The first term, here indicated as Ry, consider the lateral errors and mathematically is expressed through this piecewise function that takes this shape. So if the lateral error exceeds a threshold of 0.5 meter, then there is a very negative reward. While if the lateral error is between two thresholds, then the reward is positive and increases as the error is decreasing. Finally, the reward given by this first component is positive and constant if the error becomes smaller than a second threshold. The reason for saturating the reward when the error is small is to increase the convergence time of the cumulative reward by avoiding the exploration of action that leads to very small lateral errors in simulation, but that cannot be obtained in practice because of sensor limitations. The second component of our reward function is somehow similar to the first one, but here we consider the heading error. Instead, the third component of the reward function is a penalty based on the control action, which, as I said before, is the derivative of the steering angle. This penalty is used to help the training to find control strategies or policies that promote smooth variation of the steering angle. Or, in other words, this penalty helps to avoid chattering phenomena or high-frequency components on the steering angle. The fourth component is a term based on an expert demonstrator. In our framework, the expert demonstrator is the control action provided by an optimal linear quadratic regulator, LQ, that has been tuned using the nominal model of the QCar and can obtain in simulation a very precise tracking of the path used for training. And the fourth component of our reward function is a penalty between the mismatch. The mismatch is a penalty between the difference or the mismatch that we can have between the steering angle requested by the agent and the steering angle requested by the expert demonstrator. In terms of some details, we can say that for emulating the environment and for the control design of the expert demonstrator action, we have used the experimentally validated QCar model. Furthermore, the path that we have used during training is this S-shape path, and here you can see the cumulative reward over the episode. This picture also shows that the training is quite fast and converge in about 1000 episodes. In terms of experimental campaign, the target is again threefold. First, we want to test that the agent trained in a simulation can actually impose a trajectory not considered during the training phase. And this is an important point, as there is always a mismatch between the simulation environment and the experimental environment that can generate what is known in the literature as a simulation to reality gap, which will prevent the trained agent to perform well in reality. Then we want to test the importance of the expert demonstrator to generate an agent that can experimentally impose the desired path. Or in other words, we want to test the robustness of the trained agent to paths different from those considering during the training phase. And finally, we want to study the closed-loop performance and compare the closed-loop performance obtained with the deep reinforcement learning strategy with respect to a set of standard control approaches. In particular, we want to compare the performance of the deep reinforcement learning algorithm with respect to those that are experimentally provided by the expert demonstrator. Indeed, we want to show that the learning process can improve the performance of the control strategy used for supporting the training. For the deep reinforcement learning algorithm, to test the generalization of the approach, we have selected three different paths. So we have an O-shaped path, an infinity-shaped path, and a path that is composed by two sub-maneuvers. First, we have an U-turn that is then followed by a collision avoidance maneuver. And it's remarked that this collision avoidance maneuver is inspired by the standard ISO 38882 that is used for real vehicles, but scaled of a factor 10 to consider the actual dimension, the actual size of the QCar. In addition to the deep reinforcement learning algorithm, we have tested three standard control solutions. Specifically, we have tested a classical control strategy composed by feed-forward feedback algorithms and two linear quadratic regulator controllers. The first one, here indicated as LQ-LD strategy, ED strategy, is practically the strategy that has been used for as expert demonstrator for the training. Then we have used the second LQ strategy, here indicated as LQ-CM, which is an LQ linear quadratic regulator strategy, equipped with the feed-forward control action in order to have, in principle, for the nominal model of the QCar, zero steady-state error for a constant cornering. The path obtained by the application of each controller is reported here, and these are already experimental data. And this picture shows that all the solutions are capable to keep the QCar close to the required path. However, from a deeper analysis, we can unfold the difference tracking performance among the solutions. The first analysis comes with a zoom-in of the tracking performance during the collision avoidance submaneuver. And here it is shown that the tracking performance provided by the feed-forward feedback controller is not good, is less precise compared to the remaining controllers. And if we considered the actual size, the actual width of the QCar, there would have been also a collision of the car with this corner. More insight can be obtained on the analysis through the analysis of the closed loop performance via the analysis of the KPIs. So first, we can see here that the deep reinforcement learning that is represented in this bar chart by these purple bars provides always a smaller control effort compared to the LQ solutions. So the control effort required by the deep reinforcement learning algorithm for all the paths that we are using is smaller compared to the LQ solution. And this reduction is more significant if we compare the control effort of the deep reinforcement learning strategy with respect to the LQ used for training. And this is definitely a first improvement induced by the learning process. Only the feed-forward feedback controller provides a smaller control effort compared to the deep reinforcement learning algorithm. However, if we consider the KPI for the tracking performance provided by the feed-forward feedback strategy, those KPIs are much worse compared to those obtained with the deep reinforcement learning algorithm. Furthermore, except for the root mean square error computed on the O-shape maneuver, the deep reinforcement learning provides better tracking performance also compared to those achievable via the LQ strategy, thus confirming that the learning process underlining the design of the deep reinforcement learning algorithm can improve the performance of the expert demonstrator. And the most significant improvements have been noted on the infinity shape path. For the sake of completeness, here we report some experimental, we report the lateral error for the infinity shape path, and we can clearly see that the error, the residual error provided by the deep reinforcement learning method, here represented as a solid purple line, is smaller compared to the other solutions. More specifically, the deep reinforcement learning algorithm reduced, with respect to the LQ-CM algorithm, the maximum error of 41% and the root mean square error of 43%. And these reductions are even larger when we compare the deep reinforcement learning strategy with respect to the expert demonstrator. Indeed, the maximum error over the infinity shape maneuver reduced of 53%, and then we have also a reduction of 60% in terms of root mean square error. Now, this is the final analysis that we want to present in this webinar. And as we have previously discussed, a key component of our reward function is the term weighting the mismatch between the expert demonstrator action and the action decided by the agent. In order to evaluate the impact of this contribution on the learning process and then subsequently on the closed loop tracking performance, we have trained another agent where these contributions have been removed. What we have noted is that in a simulation, the cumulative reward converges, and the agent, also without this contribution, performs well in a simulation. However, when we experimentally tested the agent trained without the information of the expert demonstrator, the closed-loop tracking performance were quite poor. For instance, in this case, in the case of a circular shape, we can see here that the agent trained with the information of the expert demonstrator significantly outperform the tracking ability of the agent trained without the expert demonstrator. More in detail, the agent with the expert demonstrator provided over this maneuver a residual error. The maximum residual error was around 2 centimeters, while the agent trained without the information of the expert demonstrator, the error was up to 60 centimeters. Hence, we can conclude that the use of the expert demonstrator has mitigated the simulation to reality gap. Finally, before concluding, I would like to show this video where we can see the deep reinforcement learning algorithm in action. And as you can see here, the QCar tightly follows the reference path. So, concluding, we can say that in this work, the QCar has been used as a rapid control prototyping platform for studying the closed-loop dynamics of innovative path tracking solutions. And the QCar has been used for highlighting, for emphasizing the unique features of these algorithms. For instance, in the case of the neural network enhanced model reference adaptive control, the experimental analysis has confirmed that the neural network contribution is fundamental in the initial transient. Furthermore, we have noted that the error reduces over the time thanks to the adaptive mechanism. In the case of the deep reinforcement learning algorithm, the QCAR has been utilized to point out the importance of the expert demonstrator during the training phase for mitigating the simulation to reality gap, and furthermore the robustness of the method, that is the capability of the agent to follow tracks not considered, or to follow path not considered during the training phase. So it's all for my side, from my side. Thank you so much for your attention, and I'm here to answer any question that you might have related to this work.
Thank you very much, Dr. Umberto. That was an amazing presentation.
Thank you.
I think we can proceed to answer the questions that may have come in from the audience. Let me just take a look at that. Okay, so we have some questions here. The first one is, could you elaborate more on the design of the benchmark controllers used for comparison in the context of deep reinforcement learning?
Sure. So practically, based. May I share my screen or?
Yeah, please go ahead.
Good. I have some backup slides that might be used for to support this point. Can you see my screen?
Yes, we can.
So here we have so practically the design of the two LQ strategy that has been used for comparing the deep reinforcement learning algorithm with the classical controllers. So here practically there is the model of the QCAR that we have previously introduced, and for both control strategy, the control action is composed by a feed-forward feedback term here, and a feedback term plus a feed-forward term. So the key difference between the LQ-ED, the LQ algorithm used for training, and the algorithm LQ-CM with the feed-forward compensator is how we compute this feed-forward action. In the case of the algorithm used for the expert demonstrator, practically the feed-forward action is computed based on the reference curvature, where here L is the length of the QCAR. Instead, this term for the LQ algorithm with the perfect compensation of the tracking gear on steady state, this feed-forward term is computed through this formula that in principle should guarantee zero tracking error for the lateral mismatch when for constant reference curvature. So, and this is basically the key difference between these two algorithms. The feedback gain instead is tuned by solving this linear optimization problem under the condition that the dynamics of the system are satisfied.
Okay, thank you very much.
Thank you.
We have a second question. I think you can just continue sharing your slides in case you may have more
Oh, thank you.
information. The second question is, could you provide more details on the identification procedure used to determine the cornering stiffness?
Good. Practically, for the cornering stiffness, we have used a two-stage identification strategy. First, we try to identify what is known as understeering gradient, which is the linear coefficient between the steady state acceleration, lateral acceleration, with respect to the steering input during a constant cornering. And then what we have done, and of course the understeering characteristic, the understeering, this understeering gradient depends both on the front cornering stiffness and the rear cornering stiffness. So somehow this coefficient is embedded, we have embedded in this coefficient both the front and the rear cornering stiffness. So in order to discern the front cornering stiffness from the rear one, we have a second stage of our identification procedure, where we try to find through a sequence of step inputs the rear cornering stiffness that best fit the transient data under the condition that the understeering gradient is kept constant and equal to the one identified during the first stage.
Okay, perfect. Our third question is, could you offer additional insights into the design of the extended Kalman filter that's part of the federated Kalman filter?
Yes, I have a slide related to this point as well. So I can show you again my screen. Can you see my slide?
Yes, we do.
So here we have a more detailed picture of the Kalman over the scheme adopted for the Kalman filter. So practically, we had the first extended Kalman filter based on the bicycle model of the QCar. And here the states are the X and Y position of the car, the longitudinal speed, the yaw rate, the side slip angle beta, and the yaw rate. And these are the states. In terms of output for these, in terms of output here, we have the X and Y position that are measured through the LiDAR, the longitudinal speed that are measured through the encoder, and the yaw rate measured through the IMU. And through this measurement, we can correct the state predicted through this extending the Kalman filter. Then we have a second Kalman filter based on a point mass that is practically based on the measurements obtained by the IMU. Practically for this filter, the X and Y position are computed as a double integrator of the longitudinal and lateral acceleration according to this formula. Again, the measurements from the LiDAR are used to adjust the prediction of this second Kalman filter. So if we look at this Kalman filter and this Kalman filter, we note that both provide the X and Y position of the car, of the Q car on the ground. So what we have done is to use a master filter to fuse together the X and Y prediction provided by the first Kalman filter and the X and Y prediction provided by the second Kalman filter. And what is interesting to note is that this approach somehow can mitigate some jumps, for instance, in the reading of the LiDAR. For instance, here I report some experimental data where the blue line are the X and Y position given by the LiDAR sensor, while the red line here is the X and Y position provided by the master filter, which is actually was able to smooth out these kind of jumps. Does this answer your question?
We'll have to wait to see if from Carl if it answers it. In the meantime, we can continue. We have more questions here as well. One of them is, what is the hardware used to run the path tracking controller, Kalman filter, etc.?
In terms of hardware?
Yeah, the question says, what is the hardware used to run the path tracking controller, Kalman filter, etc.?
All these are deployed on the QCar.
Okay. This is running on the QCar that's using the Jetson TX2
Yes.
NVIDIA board as well.
Yes.
The next question is, what is the sampling time used for the path tracking controller?
It was a 10 millisecond.
Okay, great. The next one is a question based on slide 17 in your presentation. The FFFB can perform better than the deep reinforcement learning if the vehicle model is improved. And does this require real-time model tuning?
Sorry, can you tell me again the question?
It says the FFFB can perform better than the DRL if the vehicle model is improved, which is real-time model tuning.
Well, actually, actually what you have noted is that the parameter of the model also depends on if you want some external condition. Especially for the longitudinal dynamics, we can have different results based on based also on the, if you want, the surrounding temperature. So improving the model is definitely a possible approach, and the estimation of the parameter of the model is definitely something that will make the controller more robust. But if the controller strongly is based on these estimates, then it might fail when there is a huge mismatch between the actual vehicle parameters and the one used for the controller design. And practically is somehow what the adaptive controller tries to mitigate. In the case, for instance, of the adaptive controller, the control gains are adapted based on the actual error between the reference path and the actual path. That's why we don't need a tuning of the gains based on the vehicle parameters. Instead, if, for instance, we consider a feed-forward feedback strategy, definitely we can improve the performance, but we should retune the gains of the controller more often.
Okay, perfect. There's another question here. How dependent is the DRL of the initial setup of the LQR? More aggressive LQ control can produce better tracking errors when using the DRL.
Uh, the concept is we have noted that excessively improving the LQ controller used for expert demonstrator does not have actually an effect on the results, the experimental results. Basically, also for sensor limitation in the sensors. That's why, for instance, for the reward function, weighting the lateral error, we saturate that when the error is below a given threshold. So what we have noticed that, okay, we can improve the LQ in simulation, we can have even a better results, but when we go to the experimental on the experimental field, we didn't see these improvements.
Okay, that makes sense. We have two more questions here. It is 11 o'clock, so we can also take these questions through email and answer them at a later point. I think the last question about the contouring stiffness, I think Dr. Umberto had just answered that earlier. So this does bring us to the end of the webinar. We would like to thank Dr. Montanaro once again for his great presentation. These are fantastic results. And a big thank you to everyone who attended today. Please visit our website at quanser.com and our LinkedIn page to find out more. Have a great day, everyone.
Thank you.